Here we have an important question in elasticity. The method which we will use to solve this question can be utilized in many questions later in many other chapters also. So listen to the method carefully over here. We have a ring of linear charge density lambda, and the cross section area of the wire and the Young's modulus of the material of the wire by which the ring is made is given, and the initial radius of the wire is r. We need and a charge q0 is placed at the center of the ring. We need to find out the change in radius of the wire. Now for solving this question, let us first analyze what happens. Due to this charge q0, there is charge on this ring, due to which there is a force exerted on the wire in the outward direction, due to which there is a tension developed in the inside the ring, and therefore a stress is developed in the ring. Due to that stress, we know that Young's modulus is always equal to stress upon strain. This has to be there for the material. Therefore, due to the stress, a strain is developed, due to which there is a change in configuration from the original configuration. So that change in configuration is actually the change in radius of the wire. So we now need to find out the stress in the wire first, so that we can find out the change in configuration in the radius of the wire. Now we know that whenever you need to find out the stress in a particular material, you have to cut the material from somewhere, so that you can find out the inherent tension in the material. Now this is a standard way of doing the question involving rings. You can see this method and you can apply this in all questions involving rings in which the ring's tension needed to be found out. A charge q0 is placed at the center. Let us take an element of the ring which is subtending an angle to theta at the center of the ring. Now this theta is very small, so that this mass of the ring is very small and it has very small unit charge. It has very small charge on its arc length. Now for finding out the tension, what we do is that we cut this portion of the wire to find out the tension here. The tension here will be in this direction, and here it will be in this direction. The tension in the whole ring will be same by symmetry, as there is no biasness. Now this angle is 90 degrees. This angle is theta. That means if we draw a line parallel to this line, this angle comes out to be theta. If we take this angle was 90 degree, this is theta, therefore this is pi by 2 minus theta. Now if we take the component of tension in two directions, one in the vertical direction and the other in the horizontal direction, for both the tension forces, this is not in this direction, this is like this, and this is in the vertical direction. Now the horizontal component, the tension T was this. We write this as T. This was T. This is the horizontal component of the T. This is again the horizontal component of the T. The horizontal component of these two tension forces will be same and cancel each other. So the net resultant of these two tension forces will come in the vertical direction, and since this angle is pi by 2 minus theta, this angle is also pi by 2 minus theta. Let this be alpha. Alpha is equal to pi by 2 minus theta. Pi by 2 minus theta. Therefore the net resultant force acting on this object due to the tension forces in the vertical direction comes out to be 2t cos alpha. Now alpha is equal to pi by 2 minus theta, therefore this becomes 2t into sin theta. Now let us redraw the element. This was our element. When magnified, a net force acts on this object in the vertical direction due to the tension forces, due to the resultant ring, that comes out in the downward direction, that is equal to 2t sin theta. There is a mass q0 placed at the center, so it's 2t sin theta in this direction, q naught placed here, which exerts a force on this very small element. This is a very small element, so therefore this can be considered to be a unit mass. Let us first find out the charge on this arc of the ring. We know the linear charge density of the wire to be lambda, therefore we need to find out the length of this arc, that is equal to r into 2 theta. This is the arc length. Now this multiplied by lambda gives us the charge on this wire. Therefore the net force due to repulsion of the two positive charges comes out to be in the upward direction, and its magnitude is equal to, let this be Fe. Fe comes out to be equal to k into q naught, where k is equal to 1 upon 4 pi epsilon naught, k q naught into lambda into r into 2 theta upon r square. Now this force is balanced by 2t sin theta, since after expansion this ring is at rest. Now an important thing you should keep in mind is that the ring is already expanded, so I did a mistake here. This will be equal to r dash, let this be the final radius of the wire, and this will be equal to r dash whole square. So this final force acting on this wire after it is in equilibrium will be a function of the new radius r dash of the wire. So this force will be balanced by 2t sin theta. Now sin theta for small theta can be written as theta, therefore 2t into theta is equal to k q naught into lambda r dash 2 theta upon r dash whole square. This can be cancelled from here and we write a single r dash over here. This 2 theta gets cancelled with this to give us t is equal to k q naught lambda upon r dash. Now let us write the formula for Young's modulus on the object. We know that Young's modulus is equal to stress upon strain. Stress will be equal to the force perpendicular to the cross section area, that comes out to be T, as we already know. T upon the area of cross section is given to be A, upon strain, that is change in configuration. This we are writing for the whole ring. For the whole ring we now know the tension in the ring to be T. Therefore T is already perpendicular to the area of cross section, therefore this comes out to be the stress. We divide it by the strain. The strain in the wire is always equal to, strain can always be written as change in configuration upon original config. Therefore we will write this as T upon A upon strain. Here change in configuration, that is change in length upon original length, this can be written as 2 pi r dash minus 2 pi r. This is the change in length upon original configuration was 2 pi r. Therefore this is equal to r dash minus r upon r. This comes out to be the strain. We substitute this value over here to get r dash minus r upon r was the strain. Y is equal to T upon A into r dash minus r upon r. So from here what we see is that, let us substitute the value of T over here to get Y is equal to, let us firstly change in radius we need to find out. This is equal to T r upon A y. Now this is equal to r upon A y into T, that is equal to k q naught lambda upon r dash. Therefore this is equal to r dash minus r. Therefore we can write r dash whole square minus r into r dash is equal to k q naught lambda into r upon A y. Let us call this alpha. The quadratic equation becomes r dash whole square minus r dash minus alpha equals 0. Now over here in this equation, if we solve this quadratic equation, we get the value of r dash to be equal to r plus minus root over r square plus 4 alpha upon 2. We know that r dash is greater than r since the size of the ring increases. Therefore, we remove the negative sign to get r dash is equal to r plus root over r square plus 4 alpha upon 2. This can be written as r dash is equal to r upon 2 into 1 plus root over 1 plus 4 alpha upon r square. Now, this is 1 plus 4 alpha upon r square to the power 1 by 2. Using binomial expansion, we can write this as r by 2 into 1 plus 2 alpha upon r square. We remove the higher degree terms because the value will be negligible as compared to 2 alpha upon r square since the value of alpha is very small. Now, the value of r dash comes out to be r by 2 into 2 plus 2 alpha upon r square. On seeing this, we get r dash is equal to r by 2 into 2 plus 2 alpha upon r square. We remove the 2 to get r dash is equal to r plus alpha upon r. So r dash minus r, that is the change in radius which we require, comes out to be equal to alpha upon r. Now the value of alpha was k lambda q naught r upon ay. So alpha upon r becomes k lambda q naught upon ay. This is q naught. So our final answer for the change in radius comes out to be k lambda q naught upon a into y. So this was a pretty important question, considering that we learnt how to find out the tension inside a ring and other such figures. Whenever you need to find out the tension, you have to cut the body from somewhere. So the final answer in this question for the change in radius of the wire comes out to be k lambda into q naught upon ay, where the value of k is equal to 1 upon 4 pi epsilon naught.